Hello, I'm Mr. McBrien. This is TEJ4M, Circuits 3, Voltage Drop and Voltage Dividers. Yesterday we talked about Kirchhoff's current law and unpacked it in some detail. A basic summary of it is this. The current into a node must equal the current out of a node. And we'll use some of those concepts today in what we're working on. Okay. So today we're going to talk about what a resistor does, talk about what happens to an electron as it goes through a resistor, and then re-look at that idea one more time, talking about voltage drop across a resistor, and then look at the practical application of this concept in voltage dividers. Okay, so first off, I'd like you to think about what a resistor does. Go ahead and pause the video and think this through. Okay, well, welcome back. Maybe what you responded when asked what a resistor does is that it slows down electrons. And in fact, if you add a resistor to a series circuit, current goes down, electrons slow down. So that is true. Now I'd invite you to, once again, pause the movie, think about the answer to this question, and it's only slightly different. What happens to an electron when it passes through a resistor? Okay, welcome back. Maybe you said the electron slows down when it passes through a resistor. And this is, in fact, not true. So electrons don't slow down when they go through a resistor, and we covered that over the last couple of days. The conga line principle states that the current before and after a resistor is the same. So if an electron doesn't slow down when it passes through a resistor, what does happen to it? Well, in fact, it loses energy. So you might say to yourself, well, if the current doesn't change, if the current's the same before and after, and an electron's just an electron, how can we tell that an electron has lost energy? And the answer to this comes with our voltmeter. So if we measure the voltage, the potential between a location and ground, the voltage at point 2, in other words, the potential difference between point 2 and point 4, is 9 volts. However, between point 2 and point 4, the electron passes through that resistor and loses energy. How can we tell? Well, the potential difference between point 3 and point 4 is 0 volts. So the electrons lost energy. They lost 9 volts of potential as they moved from point 2 to point 3. And we refer to this concept, all right, of current running through a resistor causing the electrons to lose potential. We call that voltage drop. And that's the subject of our conversation today. Now, it's kind of a trivial case to talk about current moving from the positive terminal of the battery to the negative terminal of the battery and saying, okay, it loses that amount of potential. That's pretty obvious. It becomes more interesting when we talk about having two resistors in series and we say, okay, well, how much potential is lost for each one? What happens in a series circuit as an electron moves through? Well, we can look at this and say the voltage difference between point 2 and point 3 is 9 volts. We know that. The question is, what happens to the voltage, to the potential as it moves from point 2 to point 5? Okay, if we were to analyze this, we can realize that the current through both resistors is the same, and we can recognize that Ohm's law applies. In other words, the current flows through the first resistor because of a potential difference from point 2 to point 5. And the current flows through this resistor because of the potential difference between node 5 and node 3. And if we know the current, we know the potential difference, right? And because they're equal, and because the resistances are equal, well, guess what? Ohm's law says that they're going to have the same potential difference between them. In other words, each one of those resistors, having equal current and equal resistance, uses up half of the potential that is used up overall. And so we can simply divide by 2 and get 4.5 volts. And if we were to take our trusty voltmeter and place it at node 5 and node 3, we'd see that the potential difference is 4.5 volts. So it's not just a theoretical exercise, we can observe it. Okay, well this probably won't shock you when we look at the idea of 3 identical resistors in series. For these, the voltage drop gets divided between them equally. The current is the same through each one. That's our conga line principle. And so we divide the overall voltage drop by 3 to get 3 volts. And again, we could observe this if we wanted to. So I've done this inside the PhET simulator. I've built a circuit closely matched to the one we just saw, measured the potential difference before the first resistor at 9 volts. After the first resistor, it's dropped by 3 volts. After the second resistor, it's dropped now by 6 volts. And if we were to measure the trivial case of putting both the electrodes after the third resistor, we would see 0 volts. In other words, each one of the resistors uses up 3 volts. You might ask yourself, okay, well, can we only do this if the resistors are identical? And of course not. So if we wanted to look at unequal resistors, we can use our same Ohm's law concept, saying the current will be the same between each one, and we can determine what the voltage will be at each point. Point 2 we know. That's trivial, it's 9 volts. But at point 5 we can see how much potential is used up. So we can get this from Ohm's law. And Ohm's law, of course, is V equals IR. So knowing the current through the 6 kilo ohm resistor, we can do a quick calculation, sum the two of them up. The overall resistance 9 kilo ohms, so it's 1 milliamp. Well, the current has to be 1 milliamp through the 3 kilo ohm resistor as well. And then we can use V equals IR to calculate the voltage seen by each resistor. So the first resistor gets 6 volts of the potential, the second one gets 3 volts of the potential. V equals IR. And if we add them together, of course, the overall potential drop, the overall voltage drop is 9 volts. So what this means is we can calculate the voltage drop across any resistor as long as we know the resistance and the current through it. So here's an example here of a voltage drop calculation. In the circuit below, the current we know to be 0.035 amps. What's the voltage drop just across R2, our labeled resistor? And so knowing that we've got 1.2 volts, we know the resistance is 10 ohms, we know the current is 0.035 amps, and we just need to find the voltage drop for that particular resistor. V equals IR, the voltage is 0.35 volts. So of that 1.2 volts, this resistor uses up 0.35 of those volts. The other two use up the rest, of course. So you might ask yourself, can we do this without the current? Do we need to know the current in order to be able to figure these things out? And the answer is no, we don't need to know the current. Let's consider this case here. We have a 24 volt power supply. We have two resistors in series. We could calculate the current and use V equals IR to figure out the voltage drop for each one of these. But in fact, we don't need to. Why? Because the voltage drop is proportional to the resistance. So all we have to do is realize that the overall resistance is 1,000 ohms. R1's 22% of that. R2 is 78% of that. And then we can say of the overall 24 volts of drop across the two resistors, 22% is from resistor 1 and 78% is resistor 2. And we can just simply do the calculation. 0.22 times 24 volts is about 5.28 volts. And then we could either subtract from 24, getting 18.2, or multiply 0.78 times 24. So we can do those calculations either way. So let's go through a quick example. Here's a simple circuit, 12 volt power supply, and 3 series resistors. So if we want to know the voltage drop across each one of these resistors, we can take the total voltage drop, in other words, the power supply voltage, the individual resistances, and do the calculation. So I've done the center one in this case because I happen to have the equation ready to go. So the voltage drop for the second resistor then would be the resistance of the second resistor divided by the overall resistance times the power supply voltage. So 12 volts times 250 ohms divided by 875 ohms. And so our overall result then, we have the first one has 6.9 volts, the second one has 3.4 volts, and the third one has 1.7 volts. Does our answer make sense? 5.1 plus 6.9 is 12 volts. So this would seem to make sense. Also, this resistance is double this one. That's double the voltage. This resistance is double this one. That's roughly double the voltage. Okay, so our answer certainly makes sense. All right. Do we have any practical applications of this concept, or is it just some silly thing Mr. McBrien is telling us about? Well, there are practical applications of voltage drop. In particular, we can save ourselves a lot of hassle simplifying our devices. Imagine we've got a device with a 9-volt battery on it, but we have a sensor we want to power that uses 2.3 volts. We'd be tempted to take another additional battery and add it to the device. It would add weight and complexity to our device. But we don't have to. We can use the voltage drop concept to get this 2.3 volts from a 9-volt battery. So what we do is we carefully position our resistors, two resistors in series, but pull the voltage from the center of these resistors to power our little device. Now we could go through a lot of complicated mathematics in order to try to figure out what output voltage we would get from a given design. I've put the expression here, and it's really pretty simple. In fact, the output potential is just the overall potential of our original battery or power supply times R2 divided by the overall resistance of R1 plus R2. So we can calculate our output voltage very easily. Let's go through an example. In this circuit, let's calculate what V out would be. Okay, so we've got our original potential at 12 volts. R1 at 500 ohms, R2 at 250 ohms. And the equation is the one given in the previous slide. We can substitute in, and we get, by my count, our output voltage should be 1/3 of the input voltage, so 4 volts. Okay, now we might ask ourselves, okay, it's great to be able to calculate the output voltage if somebody hands us a circuit. What about if we had to design that voltage divider circuit ourselves? And so this is a very common thing, to have a specific V1, for example, a robot that has a 24-volt battery, and a target Vout for a sensor or something like this. And for this situation, we need to be able to determine R1 and R2. So there's expressions specifically for this as well. So R1 is equal to R2 times V1 over Vout minus 1, and so on. If you're curious about the derivations of these things, you can work them out yourself. If you're pretty good at algebra, you can look online for them. No big deal. So let's just do an example then where we're looking at implementing this kind of sensor. So let's imagine we've got a 9-volt battery, and our sensor doesn't need much current, about 1 milliamp, but it can't work from 9 volts. It needs a 2.3 volt power supply. So the question is, how can we wire it so it's going to work correctly? Well, in fact, what we need to do is we need to deal with the problem in 2 steps, not in 1. So our first step would be to define R1. So how do we do this? Well, considering our problem of 1 milliamp of current, we know what our voltage drop is going to be. It's going to be 9 volts minus 2.3, call it 6.7 volts of voltage drop. If we assume the current through R2 is approximately 0, we can then go ahead and use Ohm's law to calculate the voltage drop, calculate R1 based on the voltage drop. So we're given a current of 1 milliamp, Vout, and our nominal voltage of 9 volts, and we need to find R1. So R equals V over I, substitute in 6.7 volts, our voltage drop that we need through R1, divided by our current, 0.001 amps. And we get 6,700 ohms for R1. So we can use any value less than that, or maybe not any value, but in a value close to this, but we make sure that it's less so that it'll allow enough current to go through our device. Okay, the next step then, once we know R1, we'll just use 6,700 amps. We need to find R2. So given R1, we can take our expression for R2 in terms of our output voltage, R1, and our input voltage, substitute in our output voltage, 2.3 volts, R1 of 6,700 ohms, divided by our voltage drop. And the answer we get is 2,300 ohms. And so this is our voltage divider design. R1 of 6,700 ohms, R2 of 2,300 ohms. And that should give us 2.3 volts of output voltage. All right, so there's how to design a voltage divider. Now, what about a different kind of circuit? What about parallel circuits? What happens with voltage drop with parallel circuits? So if I asked you to calculate the voltage drop across R1, R2, and R3, could you do it? So you can, if you want to, pause this and think about what the voltage drop will be. All right, welcome back. If you got that the voltage drop for each one of these is the same, that it's 9 volts. Good for you. Of course, this is a trivial exercise, and you're probably right now, if you didn't get this, you're saying, oh, I should have been able to figure that out. Why? Well, notice that nodes 2, 3, and 4 are all connected by wires. They're isopotential points. Same thing for 7, 6, and 5. So 7, 6, and 5 are all at 0 volts. 2, 3, and 4 are all at 9 volts. So we know that the voltage drop across each one of these resistors is in fact 9 volts. Okay, one more little trick before we wrap up for today. Let's imagine you got a 12-volt battery on your huge robot, and one of your motors needs 12. So you got a 24-volt battery on your huge robot and a 12-volt motor that you want to be able to drive from it. Should we use a voltage divider? Part B, why not? Well, in fact, there are two answers. We're only going to cover one of them today. So let's consider, though, a situation where we've got this 12-volt, 1-amp motor, because, of course, motors use lots of current. Let's imagine designing a voltage divider to support this application. And let's ask ourselves, how efficient would it be? Well, it's easy enough to do this by calculating the power dissipated by the three different components, right? So R1 will dissipate power, R2 will dissipate power, and our motor will dissipate power. But R1 and R2 just go to heat. They're just wasted. Okay, so let's try to calculate the efficiency of this then. If we sit down and use Kirchhoff's laws to figure out the current going through the devices, I think if you give it a little bit of thought, you'll pretty quickly figure out that the current through R1 is going to be 2 amps. Then we hit the voltage divider, and half of that current goes to R2, and half goes to our device, our motor. So we got 1 amp going through the motor, 1 amp going through R2, and 2 amps going through R1. We can calculate the power associated with each one of those things next. P equals IV. And so the power through the first resistor is 24 watts, right? 12 times 2. The power through resistor 2 is 12 times 1 equals 12 watts. And the power through the motor is 12 times 1 equals 12 watts. So 36 of those watts goes to heat, and 12 goes to moving our end effector on our robot. So we've got 25% efficiency, or 75% wastage of power. This is not an efficient way to work. Okay, so you might ask yourself, well, wait a sec, after all that, do we have to just put a whole bunch of different batteries on our robot? And the answer is no. There are devices for this purpose. High current devices, we would use a step-down converter instead to take that high voltage and convert it to a lower voltage. Incidentally, an Arduino microprocessor will accept 9 volts but output 5 for us, and in an efficient manner with moderate levels of current. Okay, so let's wrap up for today then. Our key points. As electrons flow through resistors, they lose energy, and this is manifested by a drop in potential called a voltage drop. We can calculate the voltage drop in several different ways, including using Ohm's law, V equals IR. We can also calculate the potential at a given node using the ratio of resistances for series resistors. And we can apply this concept in low current applications to create a voltage divider. Okay, for your homework today then, go ahead and do the circuits activity on voltage drop and voltage dividers, and complete the calculations on the voltage drop worksheet. If you're interested in more challenges and better learning of these things, I glossed over a couple of concepts. I'd encourage you to design a set of experiments investigating the effect on the output voltage in your voltage divider based on increasing the output current. And see what happens as you increase the output current in your device. See if you can explain why that happens. And once you've done that, ask yourself, is efficiency the only reason voltage dividers are only used for low current devices? Okay, that seems like a pretty big extension, but if you read through that a few times, you should be able to understand what is meant by it. You can go ahead and use an online simulator to investigate that. So there's some additional help if you need it. There are some excellent links here to movies, etc., for those of you who want to learn more. Thanks very much. Have a great night.